When a molecule of hydrogen chloride and a water molecule encounter each other, they react to form a hydronium ion, H3O+, and a chloride ion. When sodium hydroxide enters the solution, it splits into sodium and hydroxide ions. The hydroxide ion and the hydronium ion react readily with each other to form two molecules of water. Sodium and chloride ions are left in solution.
In a strong acid, strong base, the spectators just kind of go away. So for NaOH, that would be the Na+, and for HCl, that would be Cl-. They don't affect pH, so they just kind of hang out on the side. It's really the interaction between hydronium and hydroxide that gives all this power, if you will, for these reactions. So down below, I have kind of a cheesy graph that's from a strong acid, strong base titration. And you can see that it's kind of like an S-curve, all right? And the S-curve is something that sometimes people talk about with these. When it comes to strong acid, strong base titrations, there are 4 regions that you need to think about. One of them is the initial region, i.e. when you only have what you start with, which in this case is a strong acid. One of the regions is called the equivalence region, and that's where the moles of what you start with equal the moles of what you're adding. And so the moles, which is the symbol N, moles of strong acid equal moles of strong base, and for these the pH should be about 7. Then there is the pre-equivalence region, where the moles of what you start with are greater than the moles of what you're adding. And then finally, there's the post-equivalence region, where the moles of what you're adding are greater than the moles of what you started with. Now, each of these has an equation, and we'll talk about that in just a second. At equivalence, the pH of a strong acid plus strong base titration should be, and there's 3 possibilities. Well, on that graph like there, you can probably see that the pH was equal to 7. Strong acids and strong bases annihilate each other. They totally knock themselves out. And if you're at equivalence, the moles are equal. So the products will be water and some kind of neutral salt. So you could have like sodium chloride and water if it was HCl and NaOH. Nothing affects the pH. pH should be 7 for strong acid plus strong base titrations, as well as strong base plus strong acid titrations. The 4 regions of strong acid plus strong base are initial, pre-equivalence, equivalence, and post-equivalence. Now initially you have just the strong acid, so pH equals minus log concentration of the strong acid. But we're going to see, because there's so many moles things here and volumes, sometimes it's good to think about them in terms of moles of strong acid over volume of strong acid. So either way is fine. Now at the pre-equivalence region, you still have more strong acid than you have the strong base you're adding. So the equation is overall minus log NSA divided by total volume. But you have to take out the moles of strong base that have been added, because those moles of strong base go after the strong acid. NSA minus NSB is still a number larger than 0. All right, so it's not going to 0, but it is, you have less moles of strong acid than you had. And in the bottom part, you have to use the total volume. Concentration is always moles over volume, so you have to take into account both the volume of strong acid plus the volume of strong base added to that point. The equivalence point for strong acid plus strong base, as well as strong base plus strong acid, is going to be 7, and that's kind of cool. Now on the titration graph, you can see that volume is usually the x-axis and pH is the y-axis. So if you didn't know what was happening here, a lot of times you can identify a strong acid plus strong base by literally looking at that steep point of the curve where the equivalence point is. And if it's about 7, you've got a strong acid plus strong base. Strong base plus strong acid would start basic and go acidic, so it would also have an equivalence point of 7, but be an opposite S-curve. We'll see that in a little bit. Post-equivalence means now that you have more of what you're adding than what you started with. So that means for us here, more base relative to acid. pH of a strong base, 14 plus log moles of base left over divided by total volume. So again, you've got to figure out moles of strong base that are excess. So you subtract NSA from the moles of strong base, and again, you divide by total volume. Now, in all these equations, NSA, the moles of strong acid, and VSA, the volume of strong acid, those are constants for a titration. Those numbers don't change. It's what you're adding second, which in this case is strong base, that will change. So NSB and VSB are going to change. You can usually find the VSB, the volume of the strong base, like from the titration graph itself. That's the x-axis. And then remember that volume of a strong base times concentration of strong base equals moles of strong base. So if you know the volume in liters and you multiply it by the concentration of the strong base, moles per liter, that's going to give you NSB, the moles of strong base. And that's what you'll do on these different problems. So if you kind of look back a little bit here, the initial equation and the pre-equivalence region are just when you have an excess of strong acid, all right? So minus log concentration of strong acid is how you'd find the pH. You have to take out the amount of base that's been added, but otherwise they're pretty much the same. Post-equivalence is the pH of when a strong base dominates. Again, you have to take out the amount of strong acid that was present, but it's overall the pH of a strong base. So I'm hoping that these equations don't look too crazy to you. Let's do a problem. Let's say we're titrating 50 milliliters of a 0.100 mole per liter solution of HCl with 0.100 molar NaOH. And it says, what's the pH of the initial solution? Well, let's break this down. HCl is a strong acid. It's one of the 5 strong acids we talked about in the last chapter. Sodium hydroxide is a strong base. It's one of the 3 strong bases we talked to. So the initial pH then is going to be the reflection of just the HCl. Well, HCl is a strong acid, NaOH is a strong base. This is an SA plus SB titration because we're starting with an acid. We haven't added any base yet. So it's going to be the initial region of the strong acid plus strong base titration. And if you have just a strong acid, pH equals minus log concentration. Oh yes, here's another advertisement. The other 4 common strong acids, HNO3, HBr, HI, HClO4, and the other strong bases, KOH and LiOH. Yes, we might see some of these in the future, so I'm reminding you here again of which ones they are and how I recommend that you memorize them. To find the pH, pH equals minus log concentration of the acid, the concentration of HCl, 0.100, minus log 0.100, 3 sig figs past the decimal because we put a 3 sig fig number in, pH 1.000. All right, so this would be like a problem if it wanted to find the pH of a 0.100 molar HCl solution. This is what you do, no problem. That's the initial point of our strong acid plus strong base titration. What's the pH after 45 milliliters of sodium hydroxide have been added? Okay, so now we've moved past the initial point and we're somewhere either pre-equivalence, equivalence, or post-equivalence. If you don't know, you can absolutely compare moles because all of those pre, post, and equivalence regions are all about the moles. But you can see in this problem, the concentration of base and acid are the same. So we can look directly at the volumes, 50 milliliters of acid and 45 milliliters of base. We haven't added enough base here to equivalate the acid, so this will be pre-equivalence. Let's do it the right way, though, instead of just my babbling way. First of all, you really should determine the region, and you're going to find the moles of strong acid and moles of strong base, and then just compare them. And if the acid moles are greater than the base moles, pre-equivalence. If the base moles are greater than the acid moles, post-equivalence. And if they happen to be equal, that would be truly the equivalence point. So what we're going to do is we're going to do that volume times concentration thing I mentioned earlier. We're going to take the volume of the strong acid in liters, 0.050 liters, multiply it by the concentration, 0.0050 moles of HCl. And again, that number will not change for this lab. We'll do the same thing for moles of strong base, 0.045 liters times its concentration, and as we talked about, 0.0045 moles of NaOH. So the moles of strong base are less than the moles of the strong acid we start with. So NSA, moles of strong acid, greater than NSB, moles of strong base. This is going to be a pre-equivalence region calculation. Those numbers, the moles once again, pre-equivalence minus log, parentheses, and the top NSA minus NSB, and on the bottom, and make sure you put parentheses around the bottom, especially VSA plus VSB. And you should use liters, by the way. So there's the moles on the top, total volume on the bottom. The moles part, you end up with just 1 sig fig. So the pH here, minus log of all that, 2.3. Just 1 sig fig, 1 digit to the right of the 3. Don't be too worried about that part. If you can see how to plug and chug into these equations, that's the cool part. The next question says, what's the pH at the equivalence point? So equivalence means that moles of acid equal moles of base. The two things you're looking at are the same value. At equivalence, HCl and NaOH are equal moles. They've knocked each other out. And in the process, they make water, a lot of energy, but they also make sodium ions and chloride ions. Now, sodium and chloride ions are some of the pH neutral ions we looked at in the last section. They don't affect pH. All of the conjugates of strong acids and strong bases don't affect it. So that would also include nitrate, potassium, all that kind of stuff. Sodium and chloride have no effect on pH. Pure water has a pH of 7. So that's why we say that at equivalence point, you should have a pH pretty gosh darn close to 7, all right? Because water is the only pH generating species, and water has a pH of 7. That's what you should have here too. Sometimes it's nice to know the volume required to get to equivalence, and you can absolutely do that. Remember that equivalence means that moles of acid equal moles of base. So in this problem, we had this many moles of HCl. We can cancel out the moles of HCl, turn them into moles of NaOH. We can then divide by the concentration of NaOH, and sure enough, it comes out to be, big surprise, 0.050 or 50 milliliters. Now for this problem, that probably seems a little silly because as we talked about, the concentrations are equal, so the volumes would have to be equal to get to moles. However, if the concentrations were not equal, this may not be as obvious. So you can do this kind of process. Moles of acid can be turned into moles of base, and then volume of base using concentration. FYI to the wise. So now let's figure out the pH when we've added 55 milliliters of sodium hydroxide. Now, we saw in the last problem that it took 50 milliliters of sodium hydroxide to reach equivalence. We are now past 50 milliliters. We are definitely into the pre-equivalence region. So knowing that, and from before, the moles of strong acid, 0.0050, we can figure out the moles of strong base at this point. So the concentration, 0.100 times the volume, 0.0055 moles strong base. And this number is definitely bigger than this number right here. That means we're now in the post-equivalence region. The strong base is dominating. So this equation, pH equals 14 plus log, basically hydroxide, but we want to find out the net moles of hydroxide left over after the acid's been removed, divided by total volume. Logarithms get really nervous when you have zeros and negative numbers in them, so that's why we're trying to always get these values. So NSB minus NSA is a positive number. We'll divide it again by the total volume, pH 11.7. So notice how the pH jumped quite a bit there. It started at 7 at equivalence and jumped up to 11.7. These strong acids and strong bases have very sharp S-curve graphs. This is what the graph would look like. Woohoo! So anyway, initially we saw the pH of this graph was a 1.00 value, and it is. We then saw that about 45 milliliters, the pH was only up to 2.3. And again, 45 would be about there, so you can see what's happening. So not a lot of pH change up to even 45 milliliters of strong base. However, when you get to equivalence, then you jump quite a bit. pH jumps to 7. And that's because now all the acid's been knocked out and the base is also knocked out too, so you have just pure water. And then just a little bit more base past that at 55 milliliters, pH jumps to 11.7. So this is the kind of process you can do. You can take the raw values, you can put them in a program like Excel or Apple Numbers or Google Sheets, something like that, plot them out. Y-axis would be pH, x-axis is usually volume in milliliters. Kind of cool. And you get to see the S-curve. Woohoo! Strong base plus strong acid titrations are very similar to strong acid plus strong base. The difference, though, is that, of course, you're starting now with a strong base, so the pH is basic. And then as you add the acid, the pH begins to go down. Equivalence point, where the moles are equal, will still have a pH of 7. Post-equivalence now will be acidic, and pre-equivalence now will be basic. But the equations are almost identical to what you saw for strong acid plus strong base. Initially, it's a pH of a strong base, so 14 plus log concentration of base, or if you want to write it moles and volume, 14 plus log NSB divided by VSB. Now on this problem, NSB and VSB are not going to change. We're adding a strong acid, so NSA and VSA will change, but NSB and VSB will be constant. In the pre-equivalence region, you still have the strong base dominate, but you do have a little less kick because the strong acid has removed some of the strong base. So NSB minus NSA will tell you the net number of moles of strong base left over, and you divide by the total volume. At equivalence, the two are equal to each other, so the only pH affecting species is water, so the pH should be a value of about 7. And then like we saw earlier, that in the post-equivalence region, what you're adding is going to dominate over what you started with. So in post-equivalence, moles of strong acid will be more abundant than moles of strong base. Post-equivalence region pH expression is the same as the pre-equivalence region expression in strong acid plus strong base earlier. So it's minus log, essentially concentration of hydronium. You want to find leftover moles of strong acid on top divided by total volume on the bottom. So notice that SB plus SA, pre-equivalence region here, this equation, that was the post-equivalence equation in strong acid plus strong base. And the post-equivalence equation in this slide is the same as the pre-equivalence equation on the strong acid plus strong base. Equivalence is the same, and the initial point is just now dictated by strong base versus strong acid. So hopefully by thinking these through, you can see the logic to where they all pop in. And again, some of the things will be constant, like moles of what you started with and volume of what you started with. On the other hand, what you're adding will change. So NSA and VSA will change here. They're pretty chill.